Kirchhoff's laws. This is our second video about Kirchhoff's laws. In the first video, we learned what is a node, a loop, a mesh, branch, and how to identify those things in the circuit. In this video in particular, we are going to solve some numerical examples using Kirchhoff's laws, KCL, Kirchhoff's current law, and KVL, Kirchhoff's voltage law. If you have any doubt about how to identify nodes, meshes in a circuit, please watch Kirchhoff's law part 1 video. So let's get started. Here I have an algorithm that show us step by step how to solve this circuit or any circuit using Kirchhoff's laws. So first step here is to identify all sources and their polarities in the circuit. So here we can see in this circuit that we have only one source, and the polarity of this source is already assigned. We have the positive pole here, negative down here. The second step says assign a current with a direction to each circuit branch. First, let's see how many branches we have in this this circuit. Let me change the color here, so I can see that I have changing this branch here, this branch, and this branch. So my circuit has three branches, three current paths, and for each branch I'm gonna assign a current with a direction. And here it says for voltage source, let's use conventional flow. Let's go to number 3 as well. Assign and label resistor polarities using the same thing, conventional flow. The conventional flow says that the current flows out of the positive terminal of the source, travels through the circuit, and returns into the negative terminal of the source. So this is the direction of the current leaving the source according to the conventional flow, and this is the polarity of the voltage drop across the resistor when we are using conventional flow. So the tip of the arrow would point to the positive side of the voltage drop across the resistor. Here we have Ohm's law, voltage equal resistance times current. And if we solve for I, we have I equals V divided by R. Or if we solve for R, we have R equals V divided by I. So let's go back to our circuit here, and let's see again number 2. We are going to assign a current with a direction to each circuit branch. So in this circuit branch, we already have a current which is 5 amps. So we need to assign a current for this branch and for this branch. Since I'm using conventional flow, I'm gonna say that my currents flow in this direction, flowing out of the positive terminal of my source, and I'm gonna call this current I1. And the polarity, the voltage drop across my resistor, the polarity will be positive here according to the tip of the arrow here, and negative here, and this is what will be my VR, or let's write this V1. Since we have I1, we have V1 here. Okay, my current comes all the way here and finds a node right here and is going to split. I'm gonna assume my current is splitting in this way. I have one current flowing in this direction, and the other one, which is my 5 amp, is going to flow down. I'm not going to change the direction because it's already given to me the direction in this branch of my current. This one I can assign or in this direction or going into the node in the opposite direction. I'm gonna just imagine my current comes to this point and split and keep going ahead. So this current here I'm gonna call I2, and my current comes in this direction here, my same I2, and here I will have a voltage drop. The tip of the arrow is right here, so this is my positive side, my negative side, and this I'm gonna call V2. So what I did, I assigned a current with a direction to each circuit branch. I use current conventional flow. I assign and label resistor polarities. I need to do for the one that I already have a current. So the polarity for this resistor will be positive here, negative here, because the current's flowing down. And let's see, number 4. So number 4 says derive equations using KCL or KVL as follow. So let's do step 4.1. Identify all nodes in the circuit. We already talked about that pretty much, but let's go back to it. So again, I say if you have any doubt about the definitions of node, mesh, loop, or branch, please watch Kirchhoff's laws part 1, video 1. Now I'm going to just go ahead and identify the nodes. I'm not going to go over that what is a node, how to identify it. So here in this circuit we can see that we have one node right here. 3 elements connect to this node. 3 or more elements connect to a point, forms a node. I have another node here. So this node here I'm gonna call node A. This node here connects my resistor, this resistor 24 ohms, this resistor 8 ohms, and my voltage source. I'm gonna call this node B. And that's it. Those are my 2 nodes in this circuit. Now I'm gonna use KCL and derive equations for each node. Here we have our node A. I just wrote down here so we can see better the currents that are flowing into node A and flowing out of node A. And here we have 2 definitions for Kirchhoff's current law, but in the end they're all the same. Let's read the first one. The sum of currents flowing into a node is equal to the sum of currents flowing out of the node. The second definition says the sum of all currents in a node is equal to 0. But in this case, we assign a negative sign to the currents leaving the node. So let's see how we apply those rules here. So first thing, let's identify the currents that are flowing into the node and out of the node. So into the node will be, we have here current I1, as we can see right here. It is the only current flowing into node A. And what about currents flowing out of the node? We have Y2 here and 5 amps here. So we have 2 currents flowing out of the node, 1 current flowing into the node A. And let's apply the first definition here. So let's change the color a little bit here. According to this definition, we say that the sum of currents flowing, we have only 1 current, so flowing into the node should be equal to the sum of currents out of the node. Some here and some there. Since I have only 1 current here, so that will be equals to I1, and here will be equals to I2 plus 5 amps. I'm gonna drop the notation here just to be easy. So this is my equation according to this definition, the first definition. What about the second definition? The second definition says that I have to sum all currents, but in this case we assign a negative sign to the currents leaving the node. So all currents here should be equal to 0. And our currents, so I have 3 currents in this case, 1 plus 2 plus 3, and should be all equal to 0. But the currents that are flowing out of the node, leaving the node, we are going to assign a negative sign. Here and here, a negative sign. So when I fill the blanks here, I have I1, my first current. Then my second current will be negative I2 because I assigned the negative sign to it. And my third will be negative 5. And when I add all those currents here, they should be equal to 0. So if I solve for I1, I have I2 plus 5, which gives me exactly what I had before. So it doesn't matter which definition you use, in the end you should get the same equation. So I cleaned the screen a little bit so we can work on node B now. And here it is our node B, and I have the currents that are flowing into node B and out of node B. So if I look here, 5 amps is flowing into node B. The current I2 is flowing all the way into node B, and I have right here. And the current I1, so it should start from here, come to this point, so it's flowing out of node B. That is represented right here. So let's write down what we have here. So currents flowing into node B is 5 amps, and I2. Currents flowing out of node B is I1. And I'm going to use only one of those definitions. I'm going to pick the first one that I think is much easier, which is the sum into the nodes. The current equals to the sum out of the sum of currents flowing out of the node. So what I have flowing into, summing them, 5 plus I2 equals the sum of them flowing out. So I have only I1 that will be my only current on the side. And if I look here, I got the same thing I had before with my node A. Since the objective of deriving those equations is to have different equations which I can manipulate to find the unknowns in the circuit, once I see that 2 or more nodes, in this case I have node A and B here, and I have the same currents flowing into and out of the node, I only pick one of those nodes to derive the equation I need. So I see that A and B have the same currents flowing into and out of the node, and as I showed here, then they will give me the same equation. So there's no need to derive the equation for node B in this case, because I had already derived it for node A. So this is the equation, the only equation I got when I used KCL. And here I can see that I have 2 unknowns, I1 and I2. And I need at least one more equation so I can solve this problem. Here it says if you have more unknowns, the equations go to the next step, which is 4.3.1. Identify as many meshes as needed. So let's start to identify some meshes in this circuit. Let's start by picking a point. I'm gonna pick this point right here, and I'm gonna use clockwise direction, and let's trace a loop here. I'm gonna pass through the voltage source, the resistor R, the 24, and I'm closing my loop right here. And since there's no branch inside, it's also a mesh. But I have a closed circuit path here. I'm gonna call this my L1. I'm gonna stop this video right here because it's getting too big, and we continue in the next video.